Okie dokie, chemists, let's get started. So as you can see, the chemistry department finally got their stuff together and we figured out the schedule for next spring. So I am teaching two sections of 1220. One of them is at 8 a.m. and then the other one is at 10 a.m. And so my plan is for both of those is to have an hour of office hours after each of them. So, hopefully if you can put it in your schedule somehow that you can make those office hours. I do like to have office hours directly after class most days. Try to fit that into your schedule. You're able to go to either one of them, regardless of what section of mine you're in. Keep this in mind when you're scheduling. You can either choose to follow me into the darkness, that is 1220, or choose to stay away from me, whatever floats your boat. Plan is today. So I know I said that I didn't think we'd finish chapter 8 today, but in the last class I did finish chapter 8 by accident. Yep. So keep that in mind. But I wanted to point out that on Tuesday is Halloween. And so I have a special treat for you all on Tuesday. Something that you probably have never seen, but it's not food. I don't have enough food to feed all of you. But I do have a really cool demo that I'm sure you've never seen before. I will dress up. So if you want to dress up as well, that would be awesome. I mean, you guys are in college. You can do whatever you want. Like, no one's going to judge you, and this is probably the last time in your life you'll be able to have fun, so you might as well do it, and we can all dress up together. An easy costume for you would be to dress up as your favorite chem professor. All you have to do is just wear a snappy blazer and some bright pants, and you can do that. So I'm going to dress up on Tuesday. All right. Okay, we left off talking about covalent bonding. So covalent bonding is typically molecules are formed from elements that are nonmetals on our periodic table. We already talked about ionic compounds, metals and nonmetals combining. Now we're switching gears to just nonmetals. And so this is where we're building molecules. We're going to build Lewis structures here. And so we need to think about electrons sharing or atoms sharing their electrons with one another, and some details regarding that. So when we have two elements that are the exact same, like two chlorine atoms, the two electrons that are shared in that chemical bond in those two chlorine atoms, they're exactly the same because they're shared between two identical chlorine atoms. But once we start combining atoms that are not identical, that's where we have unequal sharing or polar covalent bonds. So here's an example, HCl. And so we can use our electronegativity table and scale to think about what is the relative magnitude of the electronegativity difference of the two atoms that make up a bond. And so I have some kind of tips here on the trends of the electronegativity table. Usually what I memorize is fluorine is the most electronegative, cesium's the least. Nitrogen, oxygen, chlorine, and bromine are also very, very high, but not as high as fluorine. So those are kind of ideas that you should memorize because very rarely do we actually give you an electronegativity table. The trends are basically all you need. So that idea, electrons are not shared equally. We can kind of estimate the magnitude of the difference of extent of unequal electron sharing by calculating the difference in electronegativity of the two atoms. And so my tip is if we locate our two elements that we're bonding together on our periodic table, if the two elements you're bonding together, if they're near one another on the periodic table, they're close to one another. That means they have similar electronegativities. So if you take the difference of those two numbers, you're going to get what? A small number or a big number? A small number. Versus if you subtract the electronegativities of two elements that are far away from one another, they have dissimilar electronegativities, you're going to get a difference that is a big number. And so that gives us more ionic or polar characteristics. Large differences, so far away on the periodic table, those are ionic, but mostly we'll be talking about polar covalent bonds versus if we have two elements that are similar in electronegativities, so there's very little difference, those are non-polar covalent compounds. So let's think of our common nonpolar substances like hydrocarbons, like gasoline and things like that. Hydrocarbons are made up of what two elements? Carbon and hydrogen. So if we look at the electronegativity difference of hydrogen and carbon, see how the difference is really small, it's like 0.3. And so that falls under nonpolar covalent bonds. And that makes sense in the sense of, hydrocarbons are typically those nonpolar things that we think about. So keep electronegativity in your back pocket, especially for the chapter is coming up, but especially for organic chemistry, definitely for organic chemistry. Okay, so let me show you what I mean by unequal sharing of electrons. Here are three different fluorine-containing compounds. Fluorine is our most electronegative element, and I'm bonding it to different things. In this example, I'm bonding it to itself. All right, so if we take the electronegativity difference of diatomic fluorine, we're taking fluorine's electronegativity and subtracting it from itself. So it will always have a difference of 0, right? All our diatomics will have electronegativity differences of 0. So this is a purely nonpolar compound. We can see in terms of the coloring that there's no certain area of this molecule that electrons are hanging out, that they're all kind of spread equally across the entire molecule. But that differs for our other two examples where we do have a non-zero electronegativity difference. So here in HF, we see electrons are mostly hanging out on the fluorine side, indicated on red, and even more so in lithium fluoride, where there's almost complete electron transfer here. So what I've drawn over here, because it's difficult to color things in a Word document, oftentimes we'll use these delta signs to indicate, hey, you have a increased in electron density over on this side of your molecule on the fluorine side, while leaving a slightly positive partial charge on the other side. So these delta signs, these are what we call partial charges. They're not full-blown charges. They're just like fractions of a charge, where most of your electron density is over here, not as much over here. And so we can also draw partial charges on our lithium fluoride side. It's negative on the fluorine side, positive on the lithium side. Though this one might be more of a full charges, but the same concepts here. We can have partial charges indicating where electron density is residing on our molecule. So here's another example where I have hydrogen and chlorine. So I have the partial positive on the hydrogen side, partial negative on the chlorine side, where chlorine is more electronegative. Delta signs, kind of difficult to draw sometimes, and what will be useful for us is to actually use a vector to indicate where that increased electronegativity resides. And that's where this dipole arrow comes into play, where I can replace these partial charges with an arrow instead, where the arrowhead points to the partial negative side, right? And then on the beginning of the arrow, we put a cross, where that cross looks like a positive sign, and the positive sign starts where it's slightly electropositive. All right, so we can use an arrow to show the same thing. Where these arrows, we can treat them like vectors. So depending on the magnitude of the electronegativity difference, our arrow, dipole arrow can change. So for here, HF, I can draw my dipole arrow like that to show it's partially positive over there, slightly negative over there. For lithium fluoride, I can do the same thing, but I'm going to draw the arrow bigger. I'm going to draw the arrow bigger. It's still facing the same direction, but the idea here is that the size of your dipole arrow is relative to your electronegativity difference of your two atoms, all right? So bigger electronegativity difference of your atoms, larger your dipole arrow, all right? And so these vectors will be important once we start building molecules and thinking about what they look like in three-dimensional space. We need to think about vectors in 3D space in a little bit. But don't worry, I have some analogies to help you through that next chapter. All right, so vectors, partial charges. So we have this separation of charges. I'm just showing you the arrow. So let's think about, like, numerically how we can I guess, measure the magnitude of a bond dipole, and that is through dipole moment. And so dipole moment is represented by the Greek letter mu, And we use this equation to calculate the magnitude of dipole moment. It has two factors relating to it. All right, so dipole, first, in order to produce a dipole moment, you have to have a separation of charges. They don't have to be full-blown charges like a cation and anion, but they can be partial charges like we just talked about in our previous example up here, where like HCl, these are separated partial charges, right? So that produces a dipole moment that we can calculate. So a dipole moment needs a separation of charges separated by some set distance, and typically that's your bond length. All right, so we have two factors here, Q and R, and you see that in the equation. And both of these factors relate to things we already talked about. The Q, separation of charges, is related to the difference in electronegativity of the two atoms that make up that bond dipole. All right, so Q is related to electronegativity difference, while R, your charge separation, is related to how big your atoms are, or your bond length, right? So both of those factors affect our dipole moment, all right, to different extents, and I can show that in this table here. So remember, mu equals Q times R. So if we look at a series of compounds, these are all acids, binary acids, fluorine, chlorine, bromine, and iodine, all right? And so what we see, what we measure for these compounds in real life is we see that the dipole moment decreases, that these bonds get less polar as we go from HF to HI, all right? So let's see what factor results in this. So we see that dipole moment decreases, so that means one of these factors also has to decrease, and that's what is affecting my overall dipole moment. So let's look at these. Bond length. Which one of these factors is related to bond length? Q or R? R, yes. And then electronegativity difference, that's delta En, but that is related to our Q idea in our equation. So if we look here, R is doing what as we go down the series? It's going up, bond length is increasing, but the dipole moment is doing what? It is decreasing. So does bond length explain this phenomenon? What we're observing is length goes up, but dipole moment goes down. So does the bond length explain what's happening? No, it doesn't. So bond length does not. So maybe the other term is what is explaining this change in dipole moment. So bond length is not what is explaining dipole moment difference here. What is the electronegativity difference. If we went ahead and calculated delta En for hydrogen versus the halogen that it's attached to, we see that the delta En decreases as we go down this series. And that is what's matching the decrease in dipole moment as we go down this series as well. So it's what the electronegativity difference, Q, it's the Q factor that is affecting this, this relationship that you see, that we observe experimentally here. It's not bond length, given this information, all right? So, all right, so let's see if we can't use this equation a little bit more. All right, okay. Tell me, does mu increase or decrease in these scenarios? And assume when I make these small changes, I'm not changing everything else. Everything else is staying constant. I'm just making this one change. So if I shorten a bond, how does mu change? It increases? No, it decreases because bond length is related to R. And so if the bond length decreases, then mu should decrease. Our bond dipole should decrease. Because mu is Q times R. So if R is a smaller number, then mu is a smaller number. Yes? Okay, all right. All right, bond length increase. So that means radius, or our R increases. So that means dipole moment should increase. Okay, great. If we increase our difference in electronegativity of our atoms, so we're swapping out atoms, but the bond length stays the same. Increasing delta En will increase what factor? Oh, I already wrote it. My hand is working faster than my mouth. All right, so if the difference in electronegativity increases, that means Q is increasing in our equation, so mu increases. Versus if delta En decreases, Q will decrease, so therefore dipole moment will decrease, all right? Okay, so that's how all of that works. So can you answer me this? Which of these has a larger dipole moment, A or B? What's the important factor here? Is it Q or is it R? And remember what Q and R mean. Q is delta En, R is bond length. So you should be asking yourself, because we're looking for a difference in dipole moment, which one of those factors is different? Bond length is different. Did you calculate En? No, you didn't. Why not? Do we have to? Does it matter? Does delta En for this example matter? No, because it's the same two atoms. Regardless of what you calculate, it's going to be the same number. So for both of these examples, Q is the same number. So we know that the difference is not coming from there. Where the difference is coming through is R, the bond length. Okay, so based upon what you see, which one has the larger dipole moment, A or B? A, yes, because a single bond is longer than a double bond. This is longer, this is shorter. All right, so what we've determined here is that delta En is the same for both of these, Q is the same for both of these, but the bond lengths are different. So this is the opposite of this table that we saw here. All right, wasn't delta En was describing the difference, its bond length is describing the difference. And that's related to our R idea right there. All right, so that is bond dipoles. Keep that in your back pocket. And vectors. We're not going to go too in-depth with vectors in Chapter 9, but it is important to know how they're produced. We have to have a charge separation, a difference in electronegativity. All right, so we're going to draw molecules now. I have 6 steps, and they are bulletproof. If you memorize these, you will be right every single time. All right, so we're going to use these 6 steps to draw a Lewis structure. And so for Lewis structures, we are only writing out, drawing molecules that are made from all nonmetals. We already were done with ionic compounds. Those were metals and nonmetals. They make ionic compounds. Now we're talking about molecular compounds. They're formed from all nonmetals. They form discrete particles. All right, and we can draw their structures and describe the bonding between those atoms. So these are my 6 bulletproof steps, and you will be right every single time. So my first step is you need to count the number of valence electrons from all the atoms in your formula. So for example, if I told you water, like draw the molecule water or something like that. All right, so what you would do is you would take all of the atoms that are there, inventory the total number of valence electrons you have. So for water, what are the total number of valence electrons in water? 1, 1, and 6, so 8. So you have 8 electrons to spend in drawing your structure. That's the big idea. So count all of those valence electrons, add them up. A special tip, if you are working with drawing an ion, you need to take into account that charge in your valence electron count. So if you are working with a cation, count up all the electrons and then remove electrons as necessary to make a cation. If you're working with an anion, you count up all your valence electrons, then add electrons as necessary, right? So these electrons, this is what you have to spend. All right, and we keep that number. Understand that number. All right, so once you have that electron count, next you draw your skeleton structure. So what that means is identifying what your central atom is. 9 times out of 10, the central atom is the first element written in the formula. So actually water is not, water is an example where that's not the case. So in water, oxygen is going to be our central atom. All right, so usually the central atom is written first. Hydrogen is never your central atom, all right, because hydrogen only forms one bond, and so it can never be in the center. It always has to be on the outside. But the real true way to determine what's your central atom, it's actually the most electropositive atom. That's the real definition, but most times it's the atom that's written first. All right. So once you draw that central atom, you draw all the other atoms around it, and you draw single bonds to them. right? You connect all of them with single bonds. But remember, the first two steps, we counted electrons. Those are the only electrons we're allowed to spend. So if we draw a bond, like a line, how many electrons are in a bond? 2. So for every single bond we draw, that counts as 2 electrons in a bond. And we need to take into account that. Right? So once you draw your single bonds, you may have electrons left over. So then that's when you start completing octets on your outer atoms first, and then work your way inside. All right? You always work your way outside to inside. The actual definition here is you always put electrons on your most electronegative atoms first, and then work your way towards electropositive. So that's really the order you should go in. So you put them on the outside. Then if you have leftover electrons, then you put them on the central atom. Central atom goes last. And then finally, step 6 is you check the octets of all your atoms. And if your central atom is electron deficient, that's when you start making multiple bonds. And I'll show you some examples. Okay, because I'll tell the story. This is a core memory of mine. I remember in high school when I would draw Lewis structures. I would draw them, and I'd just start drawing dots, and then I'd just stop whenever I felt like it. All right? I did not follow the 6 steps. I never knew when to make a double bond. I never knew when to stop drawing electrons. I didn't know the difference. I was like, oh, I need to complete this octet. I'll just keep drawing electrons. But there's a very systematic way we do it now. But yeah, I remember totally doing that, just kind of spraying and praying electrons on my Lewis structures in high school. Okay, here are some tips. I'm going to just speed through these. I think it's better if we just practice them. But some big tips. Hydrogen always just has 1 bond to it. All right? Halogens also oftentimes only have 1 bond to it when they're outer atoms. And it has to do with their Lewis dot structures. Remember earlier we said, oh, there's only 1 unpaired electron, so that's one bond to it. So that's something you'll see over and over again. And then we have some exceptions that we'll talk about a little bit later at the end of the slides. All right? And then I have some other tips as well, and we'll talk about this a little bit later. What we need to be understanding is we need to both check octets, and then sometimes we need to talk about formal charges, which I will define in a little bit. So let's do a Lewis structure. Ammonia. So here are my 6 steps. All right, so after we count, make our skeleton, if we have leftover electrons, where do we place them? On the central atom? Outer atoms first. Outer atoms first, then we put them on the central. Okay. So let's look at ammonia. I take inventory of all of my atoms. I have a nitrogen and I have 3 hydrogens. Nitrogen has how many valence electrons? 5. Where did you get that? On the periodic table. And then hydrogen has 1. But there's 3 of them, so it's 3 times 1. So I have 8 electrons to spend. Right? 8 valence electrons to spend. So I did my valence electrons. Do I need to adjust for charge? No, it's a neutral thing, so 8, that's all. If it was a cation, we'd remove electrons. If it was an anion, we'd add more electrons, but we don't have to do that because it's neutral. So now we need to draw the skeleton structure. What is my central atom? Nitrogen. Okay, so nitrogen's my central atom for 2 reasons. It's written first, and hydrogen can never be the central atom, ever. So hydrogens will always be on the outside. So nitrogen's in the middle, and so I'm going to draw those 3 hydrogens around it, and then draw single bonds to all of them. All right? Okay. So how many electrons have I drawn so far? 6, because I've drawn 3 bonds. So that means I have 2 more electrons to go. So I'm going to use those 2 electrons to complete the octets of the outer atoms first, then the inner atoms. So let me ask you, does hydrogen, based upon our boy Gilbert Newton Lewis, does hydrogen have a complete octet? Yes, it does. Yes, because Gilbert Newton Lewis said the octet rule doesn't mean always 8. It means usually 8 for like, you know, row 2 elements, but for hydrogen it only needs 2 electrons because of our helium noble gas configuration. So hydrogen already has satisfied octets. Hydrogen only ever needs 1 single bond and no lone pairs. So we're done with hydrogen. So that means those 2 electrons, we don't need to put any on the outer atoms. Where are those 2 electrons going to go? On nitrogen, and that's it. Okay? And so to check now, so we've run out of electrons. At this point, you should check your octets of all of the atoms. Hydrogen, we already said, has a complete octet for all of them. Each of them has 2 electrons in each of those bonds, right? Now count the electrons around nitrogen. How many electrons does nitrogen have? 8. 1, 2, 3, 4, 5, 6, 7, 8. So nitrogen also has a complete octet. So this is a good Lewis structure. We're done. All right, so ammonia is nitrogen in the center with a lone pair and then 3 bonds to hydrogen, and that's it. All right, so we did not need to do step 6. See, it's only place double bonds if needed, meaning typically if needed means that your central atom is electron deficient. Essentially meaning your central atom does not have a complete octet. And we'll do an example of that in a minute. All right, okay, so that's ammonia. Actually, yeah, well, the next one, I think. Okay, so let's do this one, formaldehyde. So let's get the 6 steps, because it's brand new. It's brand new to us. Whoops. So let's count our valence electrons. Carbon, 2 hydrogens, and an oxygen. So carbon has 4, 2 times 1, and then oxygen has 6. So I can spend how many? 12, right? Yeah, 12 valence electrons. Okay, cool. All right. So we did our first 2 steps. Now we do the skeleton structure. I told you what the central atom is, but again, it's the most electropositive atom, and so that in this case it's carbon. Carbon's our central atom, and now we write the atoms for all of the other atoms that we didn't write so far. So I have 2 hydrogens and an oxygen. I only draw single bonds. That's my skeleton structure. All right, just single bonds. So how many electrons have I used so far? 6. How many do I have left to spend? 6. So now I need to complete the octets of outer atoms first. So where am I going to put my leftover electrons? Oxygen. So oxygen right now has 2. So if I put the 6 right here, 1, 2, 3, 4, 5, 6, it completes that octet, right? Yes, okay, cool. I didn't have to put any on hydrogen because they have complete octets already. Okay, so looking at that, these outer atoms have complete octets. There's 12 electrons there. I have no more to spend. If I was in high school, what I would do is I would do that. Okay? That's what I would do in high school. But why is that what I written in pink wrong? Yeah, that's too many electrons. But see, what I would argue is, well, carbon needs a complete octet, doesn't it? So I'm going to just draw 2 more dots. But see, I'm not going to complete carbon's octet that way. This is where I use the last step. Start making double bonds if necessary. And now it's necessary because carbon, right now, as drawn with the 12 electrons, has how many electrons around it? Not 8, but only 6. So if I make an additional bond to carbon, that's how I can make carbon have 8 electrons. So I'm not going to draw more electrons. I'm just going to move electrons around that I already have on the structure. So what you do is you take an adjacent atom. In this case, it's oxygen. And I'm going to move those electrons right there. Right? So instead of just being on oxygen, that lone pair, I'm going to make oxygen share its electrons with oxygen or with carbon, so it fulfills the octet of carbon. So I actually need to redraw this, where carbon now has a double bond to oxygen, but then how many lone pairs are left on oxygen? 2. So you got to be careful there, all right? And then those hydrogens are still there, all right? And so now if you count, do I still only have 12 electrons on that page? Yep, there's still 12, but now does every atom have a fulfilled octet? Yes, it does. Yeah, and so that's how I fulfill octets. When your central atom is deficient, just start making double bonds, basically moving lone pairs into bonds with that electron deficient atom. That's what we're doing. We're just moving electrons. We're not spraying and praying like I did before. All right, so that is what our structure would be. Will we ever see a double bond between a hydrogen and our central atom? No, you will never see that. Okay, hydrogen, it just makes one bond and then it's done. It's done. Okay. All right, so that's formaldehyde. Right, so those are our 6 steps. Learn them. We'll do some more examples here. Okay, so sometimes choosing the right Lewis structure is a little bit harder than anticipated. This is where my spraying and praying came about. I never knew what was the correct Lewis structure, but there's actually a way to figure out what is your correct Lewis structure, and it's by inspecting each of your atoms that are in your Lewis structure and pretending like they're ions. They're not really ions, but we're just going to pretend for a moment that they're ions. And what a correct Lewis structure will do is minimize what we call formal charge of those atoms. So the charge that those atoms would have if electrons were considered those full charges. So how we assign formal charges, we need to actually calculate the formal charge of every single atom in your structure. All right, so you want to do this for each atom. All right, and so to calculate the formal charge of an atom in your Lewis structure is you take the number of valence electrons that that atom usually has. So that's from your periodic table. Okay, and then you subtract the number of electrons assigned to that atom based upon the Lewis structure that you drew. So you want to look at your Lewis structure, and you want to count half of the bonding atoms, but all of the non-bonding atoms on that atom. So for example, if I had an atom, if it was like this, if I had an atom with 2 lone pairs and 2 single bonds to it, if it looked like that, I would count all of the lone pairs. So there's 4 electrons coming from non-bonding domains. But then I would only count 1 of the electrons from each of the single bonds. So this atom has 6 electrons assigned to it. All right. So that's how you calculate formal charge. All right. And then how we decide whether a Lewis structure is correct or not is we look at the full structure, all of the formal charges. A correct Lewis structure will always minimize formal charges, where 0 is the most preferred number. Okay? But sometimes you have to have a formal charge, especially if the molecule is already charged. Right? Sometimes you have to have a formal charge present. And if you do, if there's a formal charge present, the best structure will put that formal charge, if it's negative, on the most electronegative atom. If the formal charge is positive, then it'll put it on the most electropositive atom. All right? So 0 is preferred. That's the idea here. All right? And this will help us decide between Lewis structures that look both correct and you don't know which one's the most correct. All right? Is when we use formal charges. Okay. So this equation is not given to you on exams. Oh, actually, I forgot to mention. You're actually only given one equation on midterm 3. One equation, and it's this one, because I already looked at the exam, so it's this. This is the only equation that you're getting on midterm 3. It's the dipole moment equation. All right? Actually, did you see what I posted yesterday? Yes, the midterm 3 practice midterm. So they are already posted for you. All right? And the supplemental information for midterm 3. All right, so you know exactly what you're going to get, and basically it's just that equation and a weird squiggly diagram that we will talk about in chapter 9. Those are the only things that you'll need. I doubt you'll even need a calculator at midterm 3. Honestly, I'm going to tell my TAs, if you see a student on their calculator too long, that's sus, because there's nothing to calculate. Okay, so just pointing that out. All right, so let's go back to formal charge. So that means you're not given the equation for formal charge. But I have a better way to memorize the equation for formal charge. All right? To calculate formal charge, you want to take each atom and you want to take the number of electrons that that atom wants, meaning valence electrons from the periodic table, and then subtract the number of electron that that atom has in the Lewis structure. So formal charge is wants minus has. Okay? Do not confuse this with octet. All right, we're not talking about octets anymore. We're talking about valence electrons and electrons on a Lewis structure. So rarely should you ever write the number 8 for these calculations. All right, so let's look at ammonia and formaldehyde again and check if these are the correct Lewis structures or not by calculating the formal charges of all of the atoms in it. So we need to look at all of the atoms individually. So let's look at ammonia. So remember, formal charge is wants minus has. Wants comes from your periodic table, so valence electrons, and has comes from your Lewis structure. But remember, this is the tricky part, all bonds, what we want to do is all the bonds, a bond has how many electrons? 2. So when we calculate formal charges, this is what I think, you split the bond back into 1 electron and 1 electron like this. So 1 electron goes to each atom. And so when we calculate has, what we just want to do is circle, okay, this hydrogen has 1 electron because it took half of the electrons from that bond, right? Same thing for the other hydrogen. All the hydrogens are identical. But in this example, nitrogen has 3 single bonds to it, but only takes half of the electrons, so it only takes 3. But then it has that lone pair of electrons where all of those electrons are its electrons, right? And so that's where that formal charge equation comes from. You only take half of the bonding electrons, but all of the non-bonding electrons. So when we calculate has in this example, you count the number of electrons in the box, the green box that I just squared, right? So in ammonia, we have hydrogen and we have hydrogen and nitrogen. Nitrogen and hydrogen, all right? All the hydrogens are identical, so I'm just going to do 1 hydrogen. So tell me, if we're talking about a nitrogen atom, how many electrons does it want in its valence shell? 5. It's just the number of valence electrons, so 5. It's in group 5. Hydrogen wants how many? 1. Okay. Now we looked at the Lewis structure, and this is what we subtract. So tell me, how many electrons are in nitrogen's green box? 5. And then in hydrogen? 1. And so when we do the subtraction, what do we get? 0. And is that good? That is good. Yeah, 0 is good. Okay. So that's how we can be confident that this Lewis structure is correct for ammonia. But I will say, if you follow the 6 steps, you will be right in terms of Lewis structures most of the time. I have some examples where it's a little bit less clear. All right, so let's do formaldehyde now. Same thing, wants minus has. There's 3 different types of atoms here. We have a hydrogen, carbon, and an oxygen. I need to do that, okay. And so we inspect all of those separately. And again, all of the bonds, half go to one atom, half go to the other atom. So I like to draw it like this. All right, and so that double bond has a total of 4 electrons. So that means 2 electrons go to this carbon, 2 go to that oxygen, all right? So half go to each atom, and then this hydrogen goes like that, all right? And then I'll just draw the boxes again so you can clearly see how many electrons are assigned to each atom in this Lewis structure. Okay, so hydrogen, how many electrons does it want? 1. Again, so valence electrons. Carbon wants 4, oxygen 6. What a lot of students will try to do is put like 2, 8, 8, 8. They'll put a lot of 8s because they think it means octet. Maybe formal charge equal wants minus has isn't a very good thing. If you come up with a better, I don't know, analogy, I'm open to it. So wants is just number of valence electrons. Has is based upon the Lewis structure drawn. So tell me, how many dots are inside hydrogen's box? 1. Carbon, 4, and oxygen, 6. So we add those up and or subtract them, and it's 0. Is that good? Yeah, so that is good. Zeros are good. So this tells us that this structure of formaldehyde is a valid one, that it is most stable because we've minimized formal charges. Okay, so let's look at an example where it's not all zeros. Yeah. Oh, it's the same hydrogen. It's the exact same. I could. Yeah, I can do the other hydrogen. It's just the exact same. Yeah, that's why I only did one hydrogen here, because all of them are the exact same. Yeah, they're all zeros. Okay, so let's do an example where sometimes maybe it's not 0. Okay, so here's carbon dioxide. Okay, so can you just humor me for like a little bit? Because I feel like most of us know what CO2 looks like. You've seen pictures of it already, right? Like we did bond enthalpies, and we showed you pictures that CO2 is a carbon in the middle with 2 double bonds to oxygen. So let's use the 6 steps to get there, but it's a little bit muddy to get there, all right? It's gonna be a rough ride, all right? So just humor me for a second and pretend you don't know what CO2 looks like, right? So let's just go through those 6 steps. Okay, so 6 steps. Can I copy it? All right. Well, the 6 steps, first thing is we add up valence electrons. So how many is that? 16? Is it 16? Someone nod. Yes? Okay, good. All right, so 16 valence electrons. So now I need to decide my central atom. So what is it? Carbon, because it's written first and it's the most electropositive atom or least electronegative atom. So carbon's going to go in the middle, oxygen on the outside, 2 single bonds. Okay, again, humor me. Pretend you don't know what CO2 looks like. Okay, so I've drawn 4 electrons so far. How many do I have left over to spend? 12. Where am I going to put them? On the oxygens. So, and I need to complete their octets. So 4, 5, 6, 7, 8, 9, 10. That oxygen's done. 11, 12, 13, 14, 15, 16. Okay, I've run out of money. Oxygens have complete octets, but the central carbon does not. Right? How many electrons does that central carbon have right now? 4. So if we think about making double bonds to it or multiple bonds to it, how many additional bonds should I make to it to make it have a complete octet? 2 more, okay? Technically, there's a couple ways we can do it, all right? So here, I know I need to make 2 bonds to carbon, 2 more bonds to carbon. I'm just gonna move my electrons around. I'm not gonna, just see what, again, when I was in high school, all I'd just do that. But by doing that, I'm adding electrons that I can't spend. So what I need to do is move electrons around. So the first way I'm gonna do it is the way that we all kind of know what happens. I'm gonna make 1 bond by moving those lone pairs over. And I'm gonna make another bond by moving those lone pairs over. So I'm just making lone pairs into bonds. I'm not changing the number of electrons, I'm just relocating them. But technically, carbon just needs 2 additional bonds. Couldn't I also make the multiple bond coming from the same oxygen, technically? Couldn't I do this? Carbon just needs 4 more electrons, right? So in this example, I'm still completing carbon's octet. So let me just draw it, and I'll prove to you that technically both of these are correct. So in this first structure, carbon has 2 double bonds, oxygen, and then we're left with 2 lone pairs on each oxygen. In the second structure, where I moved both lone pairs from one side, carbon has a triple bond and a single bond. Oxygen, oxygen. I'm left with 1 lone pair here and 3 here. Okay. There are 6 atoms up on that board. Do any of them have incomplete octets? Any of them. So how can we tell the difference? Which one's right? And don't just say, oh, it's the double bonds because it looks better. We can't say that. It's formal charge because we literally just learned about it, right? Its formal charge is going to tell us why that one is correct. Because if your friend just said, they showed you this structure of CO2 and they were like, why isn't this correct? All the atoms have octets of 8. Like, how would you explain to them why this is not correct? We're going to use formal charge to explain why that one's not correct, because octet doesn't get us there. Because just using octet, both of these are correct. So let's do formal charge. All right, formal charge is what equation? Wants minus has. So oxygen, how many valence electrons? 6. Carbon, 4, 6. And so it's 6, 4, 6 across both of them. All right, because those just come from the periodic table. Now it's the has part that comes from the Lewis structure. So remember, each of these bonds, half of the bond electrons go to each atom. So I like to draw it like this, and then over here it looks like this. So 3 electrons go to each atom like that. All right. Oh, I did this in green, so I'll have to do the box in, I'll do the box in red. There we go. All right, so how many electrons does that oxygen have? 6. Then how about carbon? 4, and then the last oxygen? So right there, 6. So if we add that up, or subtract them, I mean, we get that the formal charges across this double bonded CO2, they're all zeros. Is that a good thing? Yes, it is. So that's why this one's correct. But let's just show why the other one is not correct. Okay, so let's do the formal charges here. How many electrons does that oxygen have? 5. Carbon has 4, and then this oxygen has 7. So we see that the formal charges are +1, 0, and -1. So remember the rules for formal charges. 0 is best to minimize formal charge, and then the second follow-up rules, if you have to have formal charges, they match electronegativities, right? So here, in this structure where we have a triple bond and a single bond, technically it does not violate the octet rule. Gilbert-Newton-Lewis wouldn't be that mad because its octets are good, but the reason it's not correct is because it does not minimize formal charges. All right, good? Good, okay, that's why CO2 has 2 double bonds. And again, so it's not guessing and checking where the double bonds and stuff goes. It has to do with formal charges. All right, so let's do a slightly harder one. NCS, anion. So we'll finally do an anion here. So if this is an anion, when we do the valence electron count, are we adding or removing an electron? How do we make an anion? Add an electron, yes. So that's weird because it's a negative charge, but we're adding negative charge. So we're adding an electron to this count, and that adds up to 16. 16? Yes? Okay. So here I tell you that C is our central atom. So I'm just going to write it exactly as it's written here. So it's NCS. Carbon's our central atom. I draw single bonds. All right, so I have 4 electrons. I need to draw 12 more. So they're going to go on the outer atoms first. So this one's tricky because there are not equivalent. The 2 outer atoms, they're not the same atom. So before, in other examples, it didn't matter where we started putting electrons first because everywhere was the same. But since these, we have the choice of putting electrons on nitrogen or sulfur first, we actually want to put electrons on the most electronegative atom first. So which atom is more electronegative? Nope. Yeah, so nitrogen versus sulfur, it's actually nitrogen is more electronegative. Because remember, fluorine is the most electronegative, and then there's 4 that are really high. Which one are those? Those are O and N, and Cl and Br. Those 4 are above 3. All right, so that would make sulfur less. So we're actually going to put electrons on nitrogen first. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. It actually didn't matter for this example which one I put it on first, but sometimes it does. Sometimes it does. Okay, so, this kind of looks like CO2, doesn't it? Yep, okay. So if you kind of see that idea here, can you see where we're going here? There's a couple ways we can fulfill carbon's octet. Because nitrogen, does it have a complete octet? Yep. Sulfur, does it have a complete octet? Yep, but carbon needs 4 more electrons, so we need to make 2 more bonds to it. But there's a couple ways we can do it. Actually, there's more ways we can do it because NCS is not a symmetrical compound. There's a couple ways we can do it. Oh, I need to make this like smaller. Okay, copy, paste. All right. There's a couple ways we can do it. Carbon just needs 2 more bonds. So couldn't I just take both, make both of the double bonds come from nitrogen? Couldn't I do that? Yeah, just like I did in CO2. What's another way I could finish the octet in carbon? Where do the electrons go? Like this? Yeah, so I could do this. 1 lone pair, make a double bond with nitrogen, make a double bond with sulfur. That's another way. And what's the other way? Both from sulfur, yes. Okay, so let's redraw these so then we can do the formal charges. So this first compound is going to have a nitrogen triple bond with how many lone pairs on the nitrogen? 1. Because I've moved these 2 as to bonds, but it leaves 1 left over. So carbon's in the center, single bond to sulfur, there are still 6 electrons there. Then I do this one, where it's 2 double bonds like this. There are 2 lone pairs still on nitrogen because I only moved 1 of them, and same thing for sulfur. Because remember, I'm just rearranging the electrons. And then this one, nitrogen has the single bond, carbon is triple bonded to sulfur. Do make sure you're keeping track of your electrons. So how many lone pairs are on sulfur? 1 lone pair, 2 electrons. Yep, like that. So if you count the electrons in all of 3 of those pictures, there are 16 in all of them. All right. Now, look at the octets. Do any of them violate the octet rule? Technically not. So how are we going to tell them apart? Formal charges. Yeah, octet's not going to tell us because they all say okay with the octet rule. So this is where we use formal charges. Okay, so what is it? Once, or your valence electrons typically on that atom, minus has. So nitrogen typically has how many valence electrons? 5. Pick a different color. 5. Carbon has 4. Sulfur has 6. So it's 5, 4, 6 all the way across. But what's different for all of them is the has part. All right? So remember, with these Lewis structures, you split the electrons. Half of the electrons in each bond go to each atom. So nitrogen has how many electrons? 5. Carbon has 4, and sulfur has 7. 1, 2, 3, 4, 5, 6, and then 1 right there. Okay. Over here, nitrogen has 6, carbon 4, sulfur 6. Again, we are splitting electrons down the middle for those bonds. Any non-bonding electrons, that atom gets all of them. All right, then this one. Nitrogen has 7, so 1, 2, 3, 4, 5, 6, 7. Carbon has 4. And then sulfur has 5. All right, now we can go ahead and subtract and then compare. So we have 0, 0, negative 1, negative 1, 0, 0, minus 2, 0, plus 1. Okay. One of these, can we just eliminate right off the bat? With the last one. Why is the last one we can eliminate? There's a lot of numbers there, right? We haven't minimized formal charges. That one only has 1 0, but all the other ones have 2 zeros. So the other 2 are clearly better than that last one. All right, so we can eliminate that one. So now let's look at the difference between the first 2 structures. We have a choice. We can put the negative formal charge on a sulfur, or we can put it on a nitrogen. Did I talk about that in terms of formal charges? Yeah. Yes, 0 is preferred, but then the follow-up was if you have to have a formal charge, it's going to follow electronegativity. So since this is a negative formal charge, we want to put that charge on the most electronegative atom. So it's a negative charge, So that negative charge will want to be on the atom that already attracts the most electrons to it. So tell me, which structure is the correct one? The first one where it's on sulfur, or the second one where the negative charge is on nitrogen? Nitrogen, yes, it's the nitrogen one. So it's the middle one. It's the middle one that looks very similar to CO2. Okay. Okay, so remember, nitrogen and sulfur, yeah, they're like near each other on the periodic table. Sulfur looks like it's closer to fluorine, but remember the rules. Fluorine is the most electronegative, but then the other four high ones are NO and Cl and Br. All four of those ones are above 3. Everything else is below 3. So nitrogen is more electronegative. So yes, this is our correct one because it puts the negative charge on nitrogen, the negative formal charge. Okay? So this is, we had to go through formal charges to figure out which one is the correct one. Right? Without doing formal charges, it would have been impossible for us to figure it out because all three of these structures have completely correct octets, right? So the 6 steps work until we need to use formal charges, where there's more than one way you can complete a Lewis structure, and that's typical if there are double bonds involved, especially if there's more than one atom where you can make a double bond, all right? Okay, so in these examples, when we made double bonds in different places, we made completely different structures. They were different formal charges on different atoms. Let's look at an example where it's not quite that way. So let's look at ozone. Okay, ozone. Hopefully you see kind of the trend here. Ozone has 18 valence electrons. So there's the skeleton structure, and I placed the electrons. Right? I stopped at step 6, where my central atom is electron deficient. So what do I have to do? What do I have to do? If my central atom only has 6 electrons, I have to make a double bond. But from where? Where? Yeah, it doesn't matter. It doesn't really matter. I could choose this one, or I could choose this one. And won't they make the exact same structures? It's just flipped, right? And that's actually what happens. It doesn't matter where that double bond is. It could be over here on this side, or it could be on this side. And they make identical compounds. That's the idea here. So these two, there's no right structure here. Both of these structures are correct. And what we actually call these are resonance structures. Because it's not that both of them are correct, but that ozone actually adopts both of these structures at the same time. The double bond isn't on the left or the right. It's not flipping back and forth. What's actually happening is that the double bond exists in both places at the same time. What we can think about is those 2 electrons that form that double bond, they're like smeared across both sides, and they exist there at the same time. So ozone is represented by what we call resonance structures. Both of these structures are absolutely correct. So this molecule exists as both structures at the same time. It is not a flipping back and forth. Okay? It's not like your molecule is becoming like short and long, like flipping back and forth. What you'll actually see in ozone is that the bonds, if you actually were to measure like the bond length or bond strength of ozone, you're going to see 2 bonds that are identical. You're going to see 2 bonds that are slightly stronger than a single bond, but not as strong as a double bond. And so we can calculate that ozone actually has a OO bond order, oxygen-oxygen bond order of 1.5. It's a little bit stronger than a single bond, not as strong as a double bond. And that's a consequence of the delocalizing electrons, the 2 electrons making up this double bond. It's on both sides. All right, so we can, that's how we're getting this fractional bond order. All right, what did I tell you at the beginning of this chapter? There are 3 ways to calculate bond order. This is the second way. Right? Keeping track? So the first way was rather easy. It was like, okay, if I draw this, what is that bond order? That's a single bond, so it's a bond order of 1. If I draw this, that's a double bond, and then that's a triple bond, yes. So those ones are obvious. It's like, oh, 1, 2, 3, but those are localized bonds that we don't have resonance there, that it's going to just stay a double or a single bond or whatever. But in resonance, we have bonds that are moving around. And so this is how I calculate resonance. I think about the bonds that are moving around in the delocalized structure. The double bond can be here or over here. So there's a total of 1, 2, 3 bonds moving around. Okay, so 3 bonds are moving around. And then I ask myself, how many resonance structures are there? Or you can think, how many total pictures, how many positions are those bonds swapping places with? So to me, there are 2 different positions that that double bond can occupy. It can either be over here or over here. So we're going to divide by 2. And so we can calculate that to be a bond order of 1.5. All right? And so again, with ozone, you can think, oh, the electron, you actually have 2 bonds that are the exact same, that are identical to one another. You don't have a strong bond and a weak bond. No, you have 2 bonds that are the same strength, and they happen to be slightly stronger than a single bond, but not as strong as a double bond. And so resonance structures happen when you have more than one correct Lewis structure. All right, and it's usually the movement of a double bond, and usually oxygen is involved with resonance structures. All right. Okay, so that is our second way we can calculate bond order. We'll look at more examples in a little bit. All right. So what's coming up next? Oh yeah, right here, nitrate. Okay. So here's another resonance. So let's use the 6 steps and then see what happens. Okay. So nitrate, nitrogen, oxygen, it's an anion. So are we adding or removing electrons? Adding. So we're going to add an electron. What does that add up to? 24, thank you. So what's my central atom? Nitrogen. Then I draw 3 oxygens and single bonds. Boop, boop, boop. All right. So I've drawn 6 electrons so far because I drew 3 bonds. So now we put electrons on the outside and complete octets. So 6. So count very carefully. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So with 24 electrons, I completed the octets of all of the oxygens. If I was in high school, I would notice, oh, nitrogen doesn't have a complete octet, so I'll just do this. But can we do that? No, we can't, because we ran out of electrons. So how are we going to fix nitrogen's deficient octet? Make a double bond from what? Any of the oxygen. So it doesn't matter, right? I can do it from the top one, the left one, or the right one. So do you see the idea that we can actually complete this this structure, this Lewis structure, from any one of those oxygens, and they're absolutely equivalent? That's how we make resonance structures. This is different from us like making double and triple bonds with formal charges. It's a little bit different here because regardless if I move electrons from there to make the double bond, or if I make it from there, or if I make it from, okay, different color, red, here, all of them are equivalent to one another, and they're actually drawn over here. These 3. These are the 3 structures. So if you think about this, each of these colors is one of these boxes. So this structure came from me moving the pink electrons to make the double bond at the top. Here, on the left side, this would be the green one, and then this is the red one. All of them are equivalent to one another. They're all equivalent, right? Because if you went ahead and calculated formal charges for all of these atoms, we don't have to, but if you did, you would actually see that we have the same formal charges, but all they do is just move around on different atoms, but they're all equivalent, right? So there's no like, oh, which is the more electronegative atom? No, they're all equivalent in terms of where the formal charges reside. Okay, so does that mean that the double bond switches from the 3 positions? Does it just like choose where it wants to be? No. It means that the double bond exists in all 3 locations at the same time. It's delocalized. I like to think that the double bond is smeared across the entire molecule. but it's easier to just write the double bond in one place when we're writing it on paper. But we have to understand that it's actually smeared across the entire molecule. Yeah?
So if, for example, if the charge is like 2 minus, would you have to put that outside the bracket?
Yes, so I actually didn't do that on the last Lewis structure. So all of these anions, the correct Lewis structure should have brackets and it should have a negative sign. Yes, at the end, for things that are charged. Yes, the correct one. Thank you. Yes, because you notice that in nitrate, all of these, because nitrate is overall negative, we have the negative charge on the outside. And if you noticed, if you did go ahead and calculate the formal charges of all the atoms here, you'll see that the total formal charge always adds up to the total charge of the molecule. All right, so that always works out. Okay, so let's look at the differences between these resonance structures. Okay, so there are 12 different atoms up here. Do they all follow the octet rule? Is there any atom that does not follow the octet rule? Nope, they're all good. Yep, so every atom follows the octet rule. All right, and so that will be true for these resonance structures that we talk about. Okay, so with the idea of what we understand with resonance structures, that it's not flipping back and forth, what is the predicted bond length of a nitrogen-oxygen in a nitrate sample? Are you going to see a short bond and a long bond? Nope, what are we going to see? All the same length, great. Okay, now let's calculate the bond order. Okay, so remember, it's number of bonds that are moving around, that are swapping places, divided by the number of positions, or you can think the number of resonance structures there are. So in this example, there are 3 resonance structures. Or you can think there's 3 different positions that that double bond can exist in. So what is the bond order? Number of bonds is 4/3. So it's 1.33, right? So in nitrate, the bond strength is going to be a little bit stronger than a single bond, not as strong as a double bond. All right? If you're wondering how I got number of bonds, I just look at one resonance structure and I count the bonds that are moving around. So there's 1 bond here, 2, 3, 4. 4 bonds moving around. Okay. So that's the second way we calculate bond order, and it's different than the other way we calculated bond order. This one's only useful for resonance structures. If you try to do this for like another molecule, it's not going to work. This is only going to work for resonance structures. Okay. Okay. All right. So let's talk about those exceptions to Lewis structures I mentioned before. All right. So, usually octet rule reigns king, but there are a few exceptions. Boron is one of them. Boron is completely okay with 6 electrons instead of 8. So BF3, where boron is your central atom, you see, oh, boron only has 6 electrons. This is okay. All right, and this is actually preferred. All right, boron with 3 bonds. All right, same thing with beryllium, but that's not as common. Beryllium, its group 2A, is fine with 4 valence electrons. So this would be like beryllium dichloride. All right, and so what we don't want to do is start making double bonds to boron to try to fulfill its octet. It's fine like this, because actually if you calculate formal charges for all of these, guess what they will be? 0 for everything, and that's preferred in this case. All right, so these elements are absolutely fine for having a deficient octet. All right, the next exception is an odd number of valence electrons. You're never going to have every atom have 8 electrons if there's an odd number. Something's going to have an odd number of electrons. So that means we will never give you this example. We will never give you an example with an odd number of valence electrons because you can't solve it using the 6 steps, because our 6 steps only work for systems that obey the octet rule. All right, so yeah, here's an example. This has NO2 neutral has a odd number of electrons, so we can't solve it. All right, so that means if you're doing homework or on the exam and you calculate an odd number of valence electrons in your first or second step, then you did something wrong and you should go back, because we would never give you one with an odd number. All right. Okay, so these ones, so yeah, do know boron is fine with 3 bonds, and that will never give you an odd number. These ones you can do. All All right, so for the most part, if you remember when we talked about Lewis structures, Lewis dot structures, we said that the octet rule works really, really, really well for group 2 elements like carbon, nitrogen, oxygen, fluorine. Works really, really well. But once things get heavier, atoms get bigger, and they can actually accommodate more electrons. And we can actually exceed their octets. And it's actually absolutely fine for that to happen. So these are some examples of group 3 elements or heavier that can have expanded octets. So for example, this sulfur atom has a total of 6 bonds to it. So there's 12 electrons on that sulfur atom. Or this xenon has 1, 2, 3, 4, 5, 6, also 12 electrons around it. So we've expanded their octets. But it's absolutely okay to do that because these atoms are big enough and can accommodate all those electrons. Also, why don't we calculate what is the formal charge of that sulfur for fun? Sulfur typically has how many electrons? 6. And then how many electrons come from bonds? 6. So its formal charge is 0. And is that good? Yes, that's good. Yeah. So we see that this SF6 compound, it actually has all 0 formal charges, and that's a good thing. But again, because sulfur is a period 3 element, it can have that expanded octet. Same thing for xenon. Even though it's a noble gas, it's big enough that if you put really electronegative things on it, it can make bonds. And actually for fun, why don't we calculate the formal charge of that xenon? Xenon typically has how many electrons in its valence shell? 8. And then let's count its electrons. How many electrons are assigned to xenon? 1 electron from each bond plus all of its lone pairs. 8. And so its formal charge is 0, and that's a good thing. Yes. And so you will only see expanded octets, we call this hypervalency, for things that are heavier than period 3, right? So like once we get to phosphorus, sulfur, chlorine, then we can start expanding our octets. So let's look at some examples. The great thing is that my 6 steps still work perfectly. You just have to know that you are allowed to expand an octet for sulfur and for bromine because they are heavy elements. So it works the exact same. It's the same 6 steps. So SF4, what does that add up to? 34, are you sure? Yeah? Okay. I believe you. Okay, so 34 electrons we can spend. Count very carefully. So we put the sulfur, we put 4 fluorines. All right, so I drew 8 electrons already. Now you need to count very carefully when completing the octets for fluorines because we need to be careful we put the right amount of electrons on that central atom. And if you don't count correctly, then you'll mess up. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So how many electrons go in my central atom? 2. There we go. Also for fun, you could calculate the formal charge of that sulfur and you will get 0. Isn't that nice? Yes. Okay, so there's SF4. So we can do the same thing for Br4 minus. So bromine, this is an anion, so we're going to add an electron. This is 36, and it's the same idea. We have bromine in the middle, fluorines around it. Count very carefully when completing the octets of the outer atom so you put the right amount in the middle. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I'm going to put 4 electrons on bromine in pairs, so it looks like that. All right? Okay. So 6 steps work perfectly every time. Yeah? No, it doesn't. Actually, it doesn't even matter how we draw our bonds for Lewis structures because they don't necessarily have to show their shape. That's chapter 9. If I wanted to draw CO2 like this, I could. I know it hurts your brain, but this is correct. This is still a correct Lewis structure. Everything still has a satisfied octet. All of my formal charges are 0. There's nothing wrong with it, right? It's not until we talk about shape. Lewis structures don't indicate shape. We have to use Vesper theory to do that. Okay, so Yeah, we have time to finish. So we've been talking about bond order a lot. So bond order, you know, a single bond, double bond, triple bond. As bond order goes up, strength goes up. But as bond order goes up, length actually goes down. All right, so strength goes up, but length goes down. So you see that for a nitrogen-nitrogen bond. We see that the strength of a nitrogen-nitrogen bond increases a lot. All right, single bond, the double bond, and the triple bond. The reasoning, in a triple bond, we have 6 electrons bringing 2 atoms together, so it's going to be a lot harder to break that guy. So we've seen these bond enthalpies before, and maybe you were aware and saw that, oh, an oxygen-oxygen single bond is a lot weaker, less as strong as an oxygen-oxygen double bond, and it has to do with the number of electrons keeping it together. So let's combine our idea, not just, you know, as bond order increases, strength increases, length decreases. Here's the strength of an NO single and double bond. Tell me, given the resonance structures of nitrate and what you understand about resonance structures, what will the measured bond strength of a nitrogen-oxygen bond in nitrate be? Are you going to measure 200 and 600 if you measure the bond strength? Or are you going to measure something else for nitrate? What are we going to measure? We're going to measure something between, because the bond order is not 1 and 2. It's actually 1.33. It's somewhere in the middle, all right? Because the bond order is 1.33. So we're going to see 3 identical bonds with the exact same strength. We're not going to see 1 strong bond and 2 weak bonds, just like in our ozone example. All right. So benzene is kind of the prototypical resonance structure you'll study. We call these aromatic rings, and that's like a whole semester in organic, you'll talk about those. All right, so benzene is another example of a resonance structure where double bonds and single bonds are swapping places. So here we have 6 carbons in a ring, and they're alternating single and double bonds. But the detail here is either the double bonds can be in these 3 positions, or you can offset them and put them in those 3 positions, right? And so it took a scientist to think about the idea of alternating single and double bonds and think, well, you know, we don't have to have those double bonds in one place. What if we just smear all of the double bonds around and delocalize all those electrons? All right, and so that's what Kekulé did. So Kekulé was, I'm assuming he was a rich scientist, because the story goes, and this is just an urban legend, I don't know if it's true or not, but he was like riding in a carriage. I hope he was a passenger, because apparently he was really high on opium. And he was looking out the window at another carriage, and he was seeing a wheel, like the wheel on the carriage turning around, all right? And again, remember, he was like high on drugs, and he was like, you know, well, what if the electrons in a benzene ring were delocalized like in a wheel of a carriage? And that's how we came up with this Kekulé structure. So this structure, the one that looks like a bolt here, this is the Kekulé structure, where we have delocalized single and double bonds. And that's his idea that, hey, they're not in localized positions, they're actually delocalized around the entire molecule. Yeah. So benzene has a bond order. Can we calculate the bond order of this benzene ring? What do you think it's going to be? It's going to be 1.5, but if we do the real calculation, there's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 bonds. 9 bonds across how many positions? 6. So that's how we get a bond order of 1.5. All right. So again, you will find carbon-carbon bonds that are a little stronger than a single bond, but a little bit weaker than a double bond. You're going to find 6 bonds that are identical to one another, and that's the theory behind what Kekulé's binge was. Right. And so here are some examples of other common resonance forms, right, that you'll see. All of these resonance structures have something in common, right? These 3 structures all have resonance. The double bond in CO3 can be here, here, or here. So if we calculate the bond order, what would the bond order be? there's 1, 2, 3, 4 bonds moving around how many positions? 3. So this has a bond order of 1.33. But let's look at acetate. Acetate has a double bond here. Where else could I put the double bond? Can I put the double bond between these 2 carbons? No, I can't, but can I put it here? Yes, you can. So there are 2 positions. So what's the bond order there? 2.5, or sorry, it would be 2 plus 1, so 3 over 2. So our bond order here is 1.5. All right, so, okay, so we didn't quite finish chapter 8, so I'm not going to make homework do. So we'll go over resonance a little bit further, but we're going to jump right into chapter 9, and I swear, if you don't know how to draw Lewis structures on Tuesday, I'm going to be real mad. I'm going to be really mad because we're still going to be doing it.